Okay, hi everyone. Today is Wednesday, and this is going to be lecture 7. This is page 1. Okay, let's look at an example. Okay, so the problem is this. There are two spaceships, each populated respectively by Alice and Bob. And each spaceship has 50 meters. Each spaceship is 50 meters long when they're both at rest. Okay, so the rest length or proper length of each spaceship is 50 meters. Pretty short for spaceships. So now I'm going to draw a figure that shows Bob's view as Alice's ship passes by at 60% of the speed of light, pretty fast. So this is Bob's view, okay? So this is his ship. And so Alice's ship looks contracted as she's passing by at speed equals 0.6 c, okay? Just as the backs of the ships pass one another, both clocks at those backs read 0. So this is the usual setup in which when the origins of two frames pass each other, the clocks located at those origins can be set to be 0. That's a convention. We can always do that. Okay, so there is a clock here that reads 0, and there's a clock right here that reads 0. So this is this 0 is a 0 in Alice's frame, and this 0 is a 0 in Bob's frame. Okay. Now here's the setup. At the instant shown, when the backs align, Bob is looking out a window that happens to be aligned with the very front of her ship. Okay, so she's moving at just the right speed that the front of her ship is aligned with this window, somewhere in the middle of Bob's ship. And, well, first of all, obviously it reads 0 here because all his clocks are synchronized. So at the instant when the backs are aligned, his back clock reads 0, so all his other clocks read 0, right? So Bob is looking out this window, he's speaking, and he sees that right at that moment, that window is aligned with the front of Alice's ship. And Alice happens to have a clock right there. And so he's speaking in, and he reads the value at the clock, value on the clock at Alice's front ship. Okay, so there's a clock. I'm going to draw a window, right? So there's a clock right there. And he's speaking in, and he's looking at the value. And so the question is, what does it read? Okay, so at the instance shown, Bob is looking out a window that's aligned with the front of Alice's ship, and he reads the clock at the front of Alice's ship. And the question is, what time does that clock show? Okay. So we will solve this problem using 3 different methods as we go along. So let's first solve it with what we already know, length contraction and time dilation. We will need both of those effects to answer this question. So first, we don't actually know the location of the window in Bob's spaceship, in his frame, that is. We do know that it's somewhere in the middle of his ship, and we do know that it's aligned with Alice's front of her ship, or the window that's located at the very front of her ship. So the window, this Bob's window, is located a distance, say delta L, from the back of his ship, right? So and this distance delta L equals the contracted length of her ship. So I guess maybe I should have reminded you that rest lengths, the proper lengths. It's also sometimes called rest length. If both ships are 50 meters. Okay, so that when the ship is parked, it's 50 meters long. Okay, so we know that his window is located this distance delta L from the back of his ship that's equal to the contracted length of her ship. Okay, so her ship also has length delta L in Bob's frame. And it has length delta L naught in her frame. I'm using the notation from yesterday's lecture. Okay, delta L equals equals distance of his window from the back of his ship, and again in his frame, which also equals the length of her contracted ship, again as seen by. Okay, so I'm writing all these qualifiers just to remind you. They might actually confuse you, but the point is, in his frame, the front window is located distance delta L from the back, and that happens to be the length of her ship as seen by him, the contracted length. Okay, now the length delta L naught equals length of Alice's ship according to her, which is just the proper length, right? So we know from length contraction okay, delta L, the contracted length of her ship, equals the proper length of her ship divided by gamma. So let's put in numbers. That's 50. Gamma is 1 over the square root. So 1 over gamma is the square root times the square root of what's inside the square root. 1 minus, and I said it's 0.6 of c. So remember, I told you that it's very convenient, and the right way of solving problems is to express speeds in units of speed of light. So you can see why this becomes convenient, because the c squareds cancel. And so, by the way, gamma equals 1.25. You can check for yourself. So then 1 over gamma is 0.8. So this is 50 and 0.8, which comes out to be 40 meters. So now we know that according to Bob, her ship looks like it's 40 meters long, and his other window is also 40 meters away from the back. Okay, so that's part one. Now, here's the key. There are two events. What are the two events? So pause the window and think about it. What are the two events that we have to focus on? The two events are the back windows align, and the event 2 is front windows align. Okay. In Bob's frame, these events happen to be simultaneous, so you think of them as one event. But we will denote them as two events because they will not be simultaneous in Alice's frame. So let me write down. Or maybe you could say that Bob's middle window is aligned with the window at the very front of Alice's ship, or just with the front of Alice's ship. So again, these events happen to be simultaneous in Bob's frame, but in Alice's frame, they're not. I'm just going to write E1 and E2. Okay, I think I should add another page here. Okay, so now what I would like to do is I would like to examine a series of snapshots as seen from Alice's perspective. Let's jump into Alice's reference frame. Okay, so this is Alice's view. This is page 2. So this is Alice's view. So this is her ship. According to her, it's 50 meters long. And these are the two windows. Okay. Now she will see Bob's ship contracted. Okay. So according to her, Bob's ship has length 40 meters, and the distance between his windows is even less because his middle window is in the middle of the ship. So what is it that she sees? What are the series of snapshots? First of all, from her perspective, his ship is moving backwards from her front towards her back. So the first interesting event is when his back window aligns with her front window. So this is the first interesting event. And it's not neither of event 1 nor event 2, what I called prior, event 1 and event 2, but it is some other event. What's the next interesting event? The next event is what I called event 2. His front window is aligned with her front window, or his middle window, rather. I'm trying to keep the lengths the same. Right? And this is what I called event 2 before. And then it's followed by event 1. He's moving back, according to her. And you can start seeing what's going on here. You can start seeing how the time dilation, non-simultaneity, and length contraction are all related. So suddenly, given that his length is contracted, it no longer seems weird that the two events are non-simultaneous. Okay, so let's continue digesting this. So event 1 is when his back window is aligned with her front window. Sometime later. I'm sorry, event 1 is when his back window is aligned with her back window. Okay, so this is, let's see if I can do this. All right, so this is something like that. And you can see that at event 2 and event 1, some of the windows are not even aligned with any of her windows. So this is event 1. And so he continues moving back. Okay. And so now note that in her frame, the distance between his windows is what? In his frame, that's 40 meters. So in her frame, that's contracted. That's 40 divided by gamma. And that's 40 over 1.45 equals 32 meters. Okay, 32 meters. So this looks like this is 32 meters. Again, according to Alex. It was 40 according to Bob. Okay, and this is one way to be sure that it takes some time. Oh, this is one way to see that it takes some time for event 1 to happen after event 2. Because you can see what's going on here. This distance right here is 50. And this distance is only 32. So it takes some time between event 2 and event 1. At the moment of event 2, the back of his ship has not yet reached the back of hers. Well, and how long does it take for event 1 to happen after event 2? What's the time difference between the two events in her frame? It's the time that's required for this back window that's a certain distance away from her back window to finally arrive here. Time between E1 and E2, according to Alice, is just distance divided by the speed, right? So it's how long it takes to cover this distance. Okay, so this is 50 minus 32 divided by the speed. So 50 minus 32 divided by 0.6 c. In other words, it's the time needed for the back of his ship to reach the back of her, the back of her ship after event 2. Now, if you crank it out, you will see that this is 10 to the minus 7 seconds, equals 0.1 microseconds. And since at that moment, it's at that moment is when her clocks read 0, it means that event 2 took place before 0. It took place when her clock, when all of her clock read 10 to the minus 10 to the minus 7 seconds. So all of her clocks 0 for 2 minus 7 seconds. Okay, because event 2 took place before event 1. So if event 1 is 0 seconds, then event 2 took place before 0, and we know how much longer before 0. We just calculated 10 to the minus 7 seconds. You know, if you want to be fastidious, you could say T1 prime equals T2 prime plus 18, which is 50 minus 32 divided by 0.6 c. Okay, and since T1 prime equals 0, therefore T2 prime equals minus 18 over 0.6 c equals minus 10 to the minus 7 seconds. But really, you don't need this. So that's, let's see. So that's basically the answer to the problem is when the front window, or when middle window of Bob's ship is aligned to the very front of Alice's ship, the clock in her ship will read 10 to the minus 7 seconds, or minus 10 to the minus 7 seconds. So when going back here, the answer to the question is that when Bob peeks into her front window, at the moment when her front window or the front of her ship is aligned with his other window, he will read minus 0.1 microsecond. Notice a few things. We had to really use a combination of the two effects, length contraction and time dilation. This is neither directly a length contraction problem, nor directly a time dilation problem. And we will see later that there's a more advanced technique that allows us to solve everything in one shot. Okay? Point number two that I want to make. Okay, so what I want to do now is I want to look at something else. So let's go back to the two ships. Alice is sitting at the back window, and Alice has her clock with her. Bob has two clocks placed at each of his windows. Exactly the scenario for time dilation. Okay, so let's check time dilation. During the time when she passes from his back window to his other window, according to Bob, how much time passed? 40 meters divided by 0.6 seconds. So during the time, I'm not going to draw pictures now. Passed from his back window to his front window. So this is 40. I'm supposed to say 40. 2.22 times 10 to the minus 7 seconds. That's Bob's clocks. Okay, so now we're tracking Alice's clock that's located at her back window. It's exactly the scenario for time dilation. So using the time dilation formula, that clock must have advanced by the following time. Okay, so the math will come out like that. Let's check that by looking at how things look like from her perspective. After the back windows align, Bob continues to move backwards. According to her, he's moving in the other direction until his other window is aligned with her back window. So she's sitting at her back window. Bob is moving back. First, she sees his back window is aligned with her. Then she sees his middle window aligned. So how much time elapses on her clock? Well, it's just distance divided by speed, okay? According to her, the distance is 32 meters. The 32 divided by 0.6 C comes out to be 1.8 times 10 to the minus 7 seconds. So you can see that the answers agree. From Bob's perspective, this is a time dilation issue. From Alice's perspective, well, it's just distance divided by the speed. But what distance? Contracted distance. Okay, so we see Bob's contracted distance. So again and again, we see that all of these effects, they work together. Okay, good. So I hope this was useful. It's a food for thought. Think about this. And now we're going to start with something else. We're going to move on to the next topic, and that's Lorentz transformations. See you.